Hi, today I'd like to continue my series on industrial gas turbine combustors. In this episode, I'd like to talk about premixed combustion. So far, we've covered diffusion flames, and in this video we'll build on that. So if you already haven't watched part 1 of this series, it'll be important to watch this first in order to understand all of the concepts I will discuss. I've included a link to this below in the description. We will focus on premixed combustion first in silo combustors. Later videos will discuss annular and canannular combustors, but each video in this series will build on the video before so that each will contain new information. As we discussed in part 1, oxides of nitrogen or NOx emissions became a concern in the latter part of the 20th century. As we saw before, nitrogen oxidizes at a rate which is exponential with temperature. Thus, the higher the flame temperature, the higher the amount of NOx produced. Diffusion flames burn over a wide range of local equivalence ratios or mixture fractions of fuel and air. This is because the fuel and air are not premixed prior to combustion. The result of this is that a large fraction of the fuel burns close to the stoichiometric ratio, or at a local equivalence ratio of 1, where the flame temperature is at its highest. Additionally, for flame stability across the full operation range of the engine, the mean equivalence ratio of the primary zone is higher than the mean equivalence ratio of the full combustor. A large fraction of air bypasses the primary zone and is mixed with the exhaust gases from the flame in the secondary zone to reduce the high temperatures of the primary zone down to the turbine inlet temperature. The result of this is that diffusion flames produce relatively high NOx emissions. Now, there are approaches to minimize these emissions, such as injecting water into the combustor, which was discussed in part 1 of this series. Aircraft engine manufacturers have also developed a number of approaches which have some success at reducing NOx emissions for diffusion flames, but all of these approaches are limited in the amount of NOx they can reduce. The theoretical minimum NOx emissions can only be achieved if the temperature in the combustor never rises above the turbine inlet temperature, and the only way to achieve this is if all of the air is involved in the combustion process and the fuel and air are perfectly premixed prior to combustion. Now, of course, perfect premixing is impractical, and no gas turbine combustor on the market achieves this. So there is a distribution of local equivalence ratio at the flame front. There are 2 reasons why it is desirable to minimize this distribution. The first, as we discussed, is to minimize NOx. If NOx emissions were linear with equivalence ratio, this would not be so important. The portions of the flame with a lower than average equivalence ratio would produce exactly the same amount less NOx as the portions of the flame with a higher than average equivalence ratio would produce. And so these 2 regions would cancel each other out, and the amount of NOx produced would be equal to the amount of NOx produced but at the average equivalence ratio. However, because NOx emissions are exponential with equivalence ratio, just an aside, NOx formation is not strictly speaking exponential with equivalence ratio. As I've said before, NOx formation is exponential with temperature. However, at the range of equivalence ratios where premixed combustion takes place in a typical gas turbine combustor, the flame temperature is close to linear with equivalence ratio. Therefore, it is reasonable to say in this region that NOx formation is exponential with equivalence ratio. The portion of the flame with a lower than average equivalence ratio produces only a small reduction in NOx, while the portions with a higher than average equivalence ratio produces significantly more NOx. Thus, the worse the premixing, the larger the equivalence ratio distribution, the higher the NOx emissions. The second reason this is important is that the equivalence ratio which corresponds to the turbine inlet temperature is already very close to the lean blow-off limit. If this distribution is too large, a fraction of the mixture will cross this limit, which might lead to portions of the flame extinguishing, and as we discussed in part 1, this can lead to high CO emissions, as CO oxidation reactions will be slowed or quenched. Additionally, in the extreme, it can also lead to unburnt fuel, as well as CO exiting the combustor, and both of these contribute to a loss in potential power for the engine. Thus, it is important to maximize the mixing and minimize the distribution in local equivalence ratio. Now, so far we've discussed the engine operating at its design point or full load. The next problem is that the engine needs to be able to operate over a wide range of loads. And as the load is reduced, the turbine inlet temperature also reduces, and the average equivalence ratio moves towards the lean blow-off limit. And this is a problem. In silo combustors, one approach to deal with this, which was the approach adopted by Brown-Boveri, is to introduce a large number of small premixed burners. As power is reduced, burners are switched off, cutting off the fuel supply to these burners, allowing the remaining burners to operate at a higher mean equivalence ratio farther from the lean blow-off limit. The air from the burners which are switched off then mixes downstream with the hot exhaust gases from the burners which are still on to reduce the temperature down to the required turbine inlet temperature. This concept works well, allowing premixed burners to be maintained down to idle, but it has a number of problems associated with it. To understand this, let's now consider how the flame is stabilized in a premixed burner. The aerodynamics of most premixed burners is very similar to diffusion burners. As was discussed in detail in part 1, the airflow is introduced swirling, producing two main regions of recirculation. One at the axis of the burner due to the vortex breakdown, and one at the sides of the burner due to the sudden expansion as the flow enters the combustion chamber. As the fuel and air are premixed, there is a burnable mixture everywhere in the combustor, and so the flame starts in the shear layer of these two recirculation zones. And the flame is stabilized in both by the recirculation of hot exhaust gases, which ignite the fresh mixture coming from the burner. Now, if we consider a series of burners side by side, and we switch one of them off, the cold air from the outer recirculation zone of the burner which is off will mix with the hot exhaust gases in the recirculation zone of the burner next to it, which is still on. This reduces the temperatures of these gases. If this temperature is reduced enough, this flow will no longer be hot enough to ignite the fresh mixture on this side of the burner, which is still on, and the flame will detach. The fuel-air mixture on this side of the burner will burn much slower, and it will be consumed eventually by the spreading of the remaining stable portions of the flame. And so if there is significant mixing between the burners which are off and the burners which are still on, there is a risk that flame stability could be significantly deteriorated. An additional issue with this is that the slower burning flame on this side of the burner will have more time to mix with the colder air from the burners which are off next to it before the combustion is complete. And this will slow the reaction rates and possibly quench reactions, which will reduce or stop the rate of CO oxidation, contributing to higher CO emissions. To minimize these problems, the location of the burners which are switched off and the swirl direction of all the burners are designed to ensure maximum mixing between groups of burners which remain on. And this way, these burners can support each other by helping to reignite any burners which encounter flame stability problems, and to minimize the mixing between groups of burners which are switched off and groups of burners which remain on. And this reduces the risk of encountering flame stability issues in the first place. One problem with doing this is that it also reduces the mixing rate between the cold air and the hot exhaust gases prior to the turbine. Now, for simplicity in this analysis, I'm ignoring the fact that the heat release in the flame causes the flow to expand and accelerate, and this can have a significant impact on the aerodynamics downstream of the burners. This effect also produces a pressure drop, which will cause a shift in the air distribution between the burners when some burners are switched off. In other words, the air will see less resistance to flow through burners which are off and more resistance to flow through burners which are on. An alternative approach to burner staging, which was adopted by Siemens for their silo combustors, is fuel staging within a single burner. This approach might be combined with burner staging also, but typically this approach requires fewer burners. Often this is done by splitting the swirler into 2 or more sections, which are each supplied with their own fuel feed or stage. If we consider a typical 2-stage system, one fuel stage is close to the axis of the burner, which is often called the pilot stage, and the other is radially further away from the axis. This may be done with a single swirler with different fuel nozzles fed from different supplies, or the 2 sections might be completely separated so that each is supplied with their own airflow as well. In this case, the design of the swirler for each can be optimized to further optimize the overall aerodynamics of the burner. At full load, both fuel stages are fed fuel, and the flame and aerodynamics of the combustor is very similar to the non-staged burner. Fuel from the inner swirler feeds the flame, which is stabilized by the recirculation zone at the center of the combustor, which is produced by the breakdown of the vortex, while fuel from the outer swirler feeds the flame, which is stabilized by the outer recirculation zone, produced by the sudden expansion of the flow. As load is reduced, the fuel to the outer swirler is switched off. This leaves only the flame, which is stabilized by the central recirculation zone. An advantage to this approach is that flow from the outer swirler, when it no longer receives fuel, will not have a direct impact on the flame stability of the flame attached to the central recirculation zone, as the central recirculation zone is fed hot gas from its own flame. The colder air from this outer swirler, though, will still mix with this flame further downstream, cooling the flame there, slowing reactions, and reducing the rate of CO oxidation. So these burners will also suffer from higher CO emissions at part load. Another disadvantage of this system is that because each burner is surrounded by cold air at part load, when the outer fuel stage is switched off, it is not possible for nearby burners to help stabilize or reignite the flame of any burner which encounters flame stability problems. Thus, it is important for this central stage to have a sufficient margin to the lean blow-off limit to avoid any flame stability issues. And this is achieved by ensuring that the stage is designed to receive a relatively small fraction of the overall burner air. Another approach to deal with this, to add some additional stability, is to add a third fuel stage, which is injected at the axis of the burner. This fuel does not burn as a premixed flame, but rather as a diffusion flame. Thus, it has all the problems associated with diffusion flames, in particular higher NOx emissions. This third stage, though, is only supplied fuel at low part load, and the amount of fuel it's supplied is relatively low. So even with this configuration, the overall engine NOx emissions can still be significantly lower than NOx emissions from older diffusion burners. Okay, so now we've discussed the motivation for premixed combustion, emissions, and flame stability. What are other problems associated with this sort of combustion? Early in the development of premixed burners, one of the biggest concerns was flashback. Because one needs to mix the fuel and air prior to the flame, there is a burnable mixture inside the burners upstream of the flame. And if the flame is able to propagate upstream into the burner, it could cause significant overheating damage to the burner. To avoid this, the velocities within the burner are maintained above a critical value to ensure that propagation due to turbulent burning velocity is not possible. One problem with this, though, is that next to the wall, due to wall friction, the velocities drop in the boundary layer down to 0 at the wall. And so this is not possible everywhere. Thus, it is important to avoid allowing a burnable mixture to exist in such regions. Adding a nozzle to the exit of the burner to accelerate the flow can help to reduce the size of this boundary layer. Another concern is the existence of recirculation zones inside the burner, which could anchor a flame if a spark or ignition source occurs there. And so burners are designed to avoid flow separation downstream of the fuel nozzles and upstream of the flame. Generally speaking, flashback is not unheard of, especially in cases where fuels are accidentally burnt, which contain higher reactive species such as hydrogen or higher order hydrocarbons than are allowed by the manufacturer for a particular burner design. But despite the initial concerns, this has really not been the most challenging issue with premixed combustion. Pulsations or combustion dynamics have been one of the biggest challenges in designing premixed combustors in gas turbine engines. Inside the combustor, pressure waves are produced by oscillations in the heat release of the flame. The flame acts like a loudspeaker. In a premixed flame, because the fuel and air are premixed prior to combustion, oscillations in local equivalence ratio can drive these oscillations in heat release. If the pressure waves produced by the flame drive the oscillations in local equivalence ratio so that there is a feedback loop, and these pressure waves correspond to a characteristic frequency of the combustion chamber, then it's possible for these pressure waves to resonate and rise to extremely high values. Now, there are other possible mechanisms to drive these dynamics, but this is the most common mechanism for premixed flames in gas turbine combustors. The problem with pulsations is that depending on their frequency and magnitude, they can cause structural components to vibrate, producing cracks in larger components and shattering seals. This is a complicated topic in itself, so I will save a more detailed discussion of this for a later video. One last challenge is the burning of liquid fuels premixed. Most modern gas turbines avoid dealing with this and have designed their premix burners to operate as diffusion flames when using liquid fuels, injecting these fuels through a nozzle in the center of the burner. Liquid fuels are generally used as backup fuels in industrial gas turbine engines, and so there has not been as much pressure from government regulators to reduce NOx emissions for liquid fuels as there has been for gaseous fuels. To burn liquid fuels premixed, the liquid fuels first need to be vaporized before they can be mixed with the air. And the temperatures of the air exiting the compressor are hot enough to achieve this. However, this requires time to accomplish, requiring longer burners, increasing the risk of flashback. There are also challenges associated with ensuring good mixing, given that liquid fuels are often injected at fewer discrete locations compared to gaseous fuel injection, and they rely on their momentum, which changes with load, to distribute. Combustion dynamics has also been found to be very challenging for such burners. The world's first premix burner for a gas turbine engine was developed by Brown-Boveri, or BBC. This went into service in 1984 on a GT13 engine in Dusseldorf, Germany. This was a relatively simple design consisting of a long duct in which fuel and air were premixed prior to encountering a swirler at the exit of the duct. Additionally, to avoid flashback, a nozzle was added to the outlet of the duct to accelerate the flow. Brown-Boveri merged together with ASEA to become ABB, and this company, together with Dr. Jakob Keller, developed one of the simplest and best performing premix burners, which became the main burner design for most of their new engines, known as the EV burner. This burner first saw service in 1993 in a GT11 engine in Midland, USA. Unlike the burner, the drawing on the patent is not simple. To make it easier to understand, I've made an axial cut through the midplane of the burner. The burner consists of a conical section, which is cut in half and then offset. Air enters the slot produced by offsetting the two half conical sections, and gaseous fuel is injected through nozzles in this slot. For operation with liquid fuel, fuel is injected to a nozzle in the center of the burner at its upstream end, and liquid fuel burns as a diffusion flame in this burner. Also in 1993, Siemens introduced their first premix burner, known as the hybrid burner, which saw service in a V94.2 engine in Sweden. This burner works on the principle of radial staging, with two independent swirlers and separate fuel feeds for both. Unlike ABB's burner, this burner has a premix mode for liquid fuel, where the liquid fuel under premixed operation is injected from the sidewall of the outer swirler. General Electric and Mitsubishi both developed premix burners in the context of canannular combustors, so we'll not discuss this technology until we get to this topic. So, in summary, premix burners were developed for gas turbine engines to minimize NOx emissions. They have the added advantage that they do not produce smoke, as there are no regions of the flame which are fuel-rich. Thus, the radiation produced by their flames, unlike diffusion flames, is relatively low, and so the cooling requirements of their combustion chambers is reduced. This is a benefit, as most of the air exiting the compressor is needed for the burners, so any cooling air which is needed to bypass the burners will result in a reduced emissions performance. These burners burn close to the lean blow-off limit at full load. Thus, it is necessary as engine load is reduced to do something to preserve flame stability. Flashback is a problem which can occur, but generally with proper design, the risk of flashback is low. Pulsations, or combustion dynamics, is one of the biggest challenges this sort of combustor has. Additionally, burning liquid fuels, premixed, is significantly more challenging than gaseous fuels, and as a result, most engines today still operate as diffusion flames for liquid fuels. Okay, so this concludes this video. In the next video, I'll explain the mechanisms which drive combustor pulsations, or dynamics, in premixed gas turbines, and discuss some of the things which can be done to avoid these issues. I hope you liked this video. If you did, please click the like button below, and if you'd like to see more videos like this one, please subscribe to the channel. Thanks.